This video introduces PyFLOSIC version 1.0.0, which is available at GitHub, and I want to guide you through the installation process and the basics. There is a documentation of PyFLOSIC at GitHub outlining the main features, for example, what it inherits from PySCF, how to generate Fermi orbital descriptor positions, and how to actually carry out FLOSIC calculations. PyFLOSIC is a Python implementation of a self-interaction correction based on Fermi Levine orbitals, which gives FLOSIC its name. What is SIC? As a consequence of using approximations to the exchange correlation functional in standard density functional theory calculations, electrons artificially interact with themselves. This is known as the self-interaction error. The cone-sham or KS energy functional consists of the kinetic energy of the non-interacting system, the external potential energy, the Coulomb energy, and, denoted here with K, the exchange correlation energy. In this context, N is the total electron density, and then alpha and then beta are spin up and spin down densities. For every one electron density, denoted here as N1, the exchange correlation part and the Coulomb part have to exactly cancel. While this is true for the exact exchange correlation functional, it is not true for approximations to it. And with that, we end up at a residual self-interaction SI error for every electron in our system. In 1981, Purdue and Zunger, PZ, introduced a self-interaction correction, which they added on top of the cone-sham energy functional. And the self-interaction correction term subtracts this one electron self-interaction error for every single orbital in the system. With that, the PZ energy functional becomes orbital dependent, in clear contrast to the cone-sham energy functional. And also it has been shown that using localized orbitals for these one electron densities delivers lower total PZ energies. In FLOSIC, these localized one electron densities or orbitals are the Fermi Levine orbitals. To obtain these FLOs, we need reference positions in space, which are called the Fermi orbital descriptors, or FODs. First of all, we construct Fermi orbitals, FO, from a rotation, denoted here as R, of the occupied orbital space. We typically use the cone-sham orbitals. The rotation matrix itself is defined in terms of these AIs, which are the FOD positions. This rotation then localizes the Fermi orbitals around these reference positions in space. There is exactly one FOD for every electron in the system. Because the Fermi orbitals themselves are normalized, but not necessarily orthogonal, the last step is a Levine orthogonalization using the eigenvectors and eigenvalues of the overlap matrix of the FOs to construct a set of localized Fermi Levine orbitals. Here we have an example of the C2CN4 molecule. In brown we have the carbon atoms, in blue the nitrogen atoms. In addition, in green we have the FOD positions of one spin channel in this system. The FOD positions of the other spin channel are at the same position. As we can see, there are situations where there is one FOD between two atoms, which corresponds to a localized orbital that can be characterized as a single bond orbital. With that, this is a single bond FOD. In between the two carbons at the center, we have two FOD positions orienting themselves perpendicular to the molecular axis. These FODs now correspond to double bond orbitals and can be thought of as double bond FODs. And between the carbons and the nitrogens, we have three FOD positions between these atoms corresponding to a triple bond between them. Further, we have single FODs at the nitrogen atoms, which are not in the bonded region. These correspond to localized lone orbitals. In summary, the FOD positions do give a picture of the bonding situation in a given molecule. Why PyFLOSIC? It is a user-friendly and transparent code promoting open science. Typically, we only develop one or a few features in a small group that we can then put together into a larger code. And using PySCF as a basis allows for very efficient code development. The development is transparent, using a combination of existing features and new features, that is, using existing Python packages and introducing new Python packages to introduce new features. As always, we promote open science. At the Git history, everyone can have a look into the details of the code and about what is happening right now. And PyFLOSIC allows for very easy Python workflows. For example, using ASE, NumPy, and SciPy allows for very simple FLOSIC calculations. To install PyFLOSIC, you only need an existing PySCF installation, which can be obtained via pip3 install PySCF. You will then need one additional download, that is Git cloning the PyFLOSIC repository from GitHub. And you need to set one path, which allows Python to know where PyFLOSIC is and how to access it. With that, we can start combining Python packages, starting at the density functional theory level, where we can exploit the functionalities of PySCF. Then we can generate initial starting points for the FODs, using, for example, FODMC, PyCom, PyEFF, or PyLewis. On top of which, we can then start the actual FLOSIC calculation using PyFLOSIC. Now I'd like to show you how you set up a FLOSIC calculation, that is, how to generate initial starting points for the FODs. In the script, we first of all import the read function from ASE and the PyCom guess function from the PyCom module. We then load the nuclear information by reading this SDF file and storing the information into an ASE object. And then we start the FOD generation. The inputs are the nuclear information, the charge and the spin of the system, an exchange correlation functional and a basis set, and a localization method for the occupied orbitals. In this case, it's Foster-Boyce. The output of this script is a single XYZ file called fb_guess_com that now contains the nuclear information as well as the coordinates for the spin up FODs and the spin down FODs. Having this file now allows us to run the actual PhLOSIC calculation. Here again, we import the read function from ASE and the PhLOSIC optimize function from the PyFLOSIC optimizer. We then load the nuclear and the FOD information by reading the XYZ file we just generated and storing all that information in an ASE object. And then we start the optimization of the density as well as of the FODs. The mode PhLOSIC SCF corresponds to us doing full self-consistent field calculations before we update the FODs. We then load the nuclear and the FOD information. We provide charge and spin of the system, an exchange correlation functional and a basis set. In addition, we provide the optimizer. In this case, it is the fire optimizer with a corresponding max step. And at last, we define a threshold for the maximum force of the FODs, which then determines when the calculation finishes. With that, I'd like you to stay tuned. We have the OpenSIC project at Twitter, where we will update news about the project. Also, we have the OpenSIC project at ResearchGate and at YouTube. With that, at the very last reminder, Python is a way to code very efficiently, and GitHub and GitLab allow us to efficiently share code with the community, that is, with you. This presentation has been done with the Web Slides tool, which is a nice and efficient way to generate presentations for the community. And with that, I would like to thank you for your attention.